start that and share. All right, is that sharing?
All we see is the connect to Wi-Fi FBI surveillance van.
Yeah, why is that? All right. There we go. Yeah. Now you can see it. Okay. Yes. Now you know our Wi-Fi name. All right. So I gotta rearrange my windows here. Just a couple of things. First, with the announcements. So today we're going to finish up this sort of overview, basically chapter 7 on ordinary differential equations. And what we're going to focus on today is using the Wronksian to find a second linearly independent solution if we know the first. So that's going to be the focus of the lecture today. Regarding the homework that's due again next week, I think I've changed all of the due dates on the Moodle page so that you get so everything's been shifted essentially a day except the last homework. So it's due on Tuesday after midterm reading period. I did want to say give 2 hints regarding the homework and change one of the homework problems. So 7.57 and 7.59 are in the section on series solutions for differential equations. And because I've had a couple of questions about this, I wanted to give you a couple of things, basically hints to help you. So 7.57, you need to find that indicial equation. It's kind of hidden in the question, but just try a trial solution for the differential equation that you're looking at as written. And then 7.59, you're looking at essentially a special case of the Schrodinger equation. So what I'm suggesting is that you try a solution of psi being a series expansion, just a regular series expansion, and then start collecting terms. Most of them will be constant terms, h bar squared over 2m and so on, and then write the potential as ax times e to the minus ax. That might allow itself for further expansion. And then when you get all of those terms, you'll be able to identify the psi expansion with all of those terms that come from that solution. I think if you haven't looked at that problem, this might make more sense when you do. So there's that. Then the last change, the last change is I'm changing the problem in chapter 7.6 that's on linear independence solutions. If you've already done 7.69, go ahead and turn that in. I don't want you to waste the effort, but that problem is more about the properties of a Wronskian. It's not an actually particularly good application. 7.6.22 is a relatively straightforward application of the Wronskian. They give you, I think it's the Legendre equation. No, it's the Chebyshev equation. And they give you one solution, and you're to use the Wronskian to find the other. And I forgot to add this, just do part A. Part B asks you to find it in a different way, and actually that's a little bit tricky because of some of the singularities involved. So that's 7.6.22 looks at the Chebyshev equation, given that one of the solutions is y is equal to 1 for the special case of n equals 0, and then you find the other using the Wronskian. It's pretty straightforward application, I hope. Any questions on the homework? We good? Okay. and I'll keep this up in case you still need to copy this. What we're going to do now is something I mentioned in an announcement to the class. One of the things that I've talked to a couple of you about is having a little bit more interaction in the class, and I would love that. I don't like just talking to a screen myself. So what we're going to try and do every day that we meet is have a short, small exercise that highlights a problem that people, especially if they've mentioned it in their weekly reflections. Based on some of the feedback on the material that we've just covered, I want to give you a chance in groups of 2 or 3 to solve this would be a non-Frobenius problem. So what I want you to do, and I'm going to put you into breakout rooms for a few minutes, is consider this differential equation, x times y prime minus y is equal to x squared, and use the general series solution to find a solution. This is a first order differential equation, so there's only one solution. And of course, you'll know you've got the right solution when you substitute it back in. Okay? So for that, I need to make sure I can make breakout rooms, which I hopefully can do. And let's see. I'll put my share screen over here. This window over here. I'm not getting my controls. Hang on a second. There we go. All right. Now, I'm going to try and do this manually so that I don't put Ines and Ben in the same room again. But we'll see what happens. So let's see. Let's do 4 rooms. And let's assign there. Breakout room 2. We'll put now that. Assign that. And then, all right. There you go. Go to your rooms, and then we'll give you about 10 minutes or so to figure all this out. Okay? Did you guys get assigned a room? There you go. There. Okay. Okay, is that everybody? We're all closed. Okay. Did you guys get a solution? No? Who did anybody want to share us? Did anybody get a solution? All right. Did you get close?
Set it up.
Okay. So how did you set it up?
So I think we have to use the Bernoulli equation looking thing since we have the f of x non-homogeneous.
Well, in this case, we're using a series solution, right? So,
Do we plug that into the?
yeah, so let's go here. What I was looking for was the following. And if you needed more time, let me know. I'm just trying this out, so it's hard for me to know if this is more time. So what we have, what
Time.
was that?
I needed more time.
Okay, all right. I'll know that for next time. Sorry. Were you on the right track?
I think we were.
Okay, so thank you, and I apologize for not giving you enough time. That's good feedback. So anyway, we have our differential equation. We have what y is. We have what y prime is. Oops. Times x. So if we look at the if we look at the three different terms of the differential equation and look at their expansions, realizing that the y prime term starts at n equals 1 in this case because we've lost the constant term. And then one way, whether you're using the Frobenius method, which is actually more useful for second order differential equations that are more complicated than this, it's good to have one column where you have the terms, right? And then another column where you have the powers of x. So x to the 0, x to the 1, 2, 3, and then start looking for, in the case of an actual series solution, what series you might actually find if it becomes a closed form. In this particular case, the series ended, right? So if you look at the constant terms, basically you only had a0, and that had to be equal to 0. So if we look at all of the different terms that go into this differential equation, that is, if we set x prime y minus x squared equals 0, then a naught plus minus nothing is equal to 0. So that means a naught is equal to 0. If we look at the terms that include x, we have a1 minus a1 is equal to 0. If we look at x squared, we have something where a2 and 2a2 is equal to minus 1, and so on. So what we end up from this is that a0 is equal to 0. A1 is equal to a constant, that is, it's completely unrestrained, and A2 is equal to minus 1. So what we have for our solution is that y is equal to some constant times x minus x squared. Okay, everybody see where that comes from?
Why is there an A0 term in the xy prime row?
Because I don't know, actually.
It
I
should be
think
with
that's
y
over
term.
here. Yeah. Right. I think I mixed up the rows, right? Because the xy prime series starts at n equals 1. Thank you. Sorry. The result is still the same. The constant goes away. And so we have this solution that's cx minus x squared. And then we can check it by computing what y prime is. So that's c minus 2x. It's just some scratch here. And then xy prime is equal to cx minus 2x squared. And then when we take x prime, x times y prime minus y, we end up with x squared, which is the solution to the differential equation. Okay, so the main idea here is that when you have your differential equation, let me shrink this up a little bit. Right. The first step is to look at what are y prime, y double prime, and then to make this kind of a table to line up, because we know that each power of x needs to have the same, those coefficients have to add up to be equal to 0. For a series that extends to infinity, that might get you a recursion relation or a relationship between one value of those coefficients and another. If you're lucky in this case and it's a straightforward or a simple differential equation, then the series is going to terminate and you'll just have, say, a polynomial. Okay. Any questions? Okay, so oh, go ahead.
So the method isn't really different whether or not it's homogeneous. It's basically pretty much the same thing, just different steps.
Yes, that's right. Mm-hmm. That's right. And if it's not homogeneous, right, then you're just basically, if it's a function of x, that just means that you are collecting, you're going to have one column that has a value that's related to that power of x. Or you could imagine that it's, say, x squared plus x. So then you would have something that's non-zero here. That might make things complicated. And it may not, but I tried to make as a kind of a straightforward model that's similar to stuff that you're going to be seeing both in the homework and, on the midterm, say. Yeah, good. Any other questions? Okay, so when on Monday, we're going to do something similar, and I'll give you a little bit more time, and I'll try and drop in on the rooms. The last time I dropped into rooms with a department meeting, I accidentally closed everything. So I was a little worried about dropping in to see how people were doing. So I'll risk it for you. Okay. All right. Let's get back to where we need to be. And again, this is all part of the recording, so you can go back and take a look at this if you need to. So now our plan here is to look at what happens when we have one solution and we want to find the other linearly independent solution. And that requires looking at what's called the Wronksian. Okay. For the first thing we're going to do is assume, well, we're going to look at what are the conditions for linear independence. And then what can we, if we have a diagnostic for linear independence, what can we do with that? So let's assume that we can write a series of solutions, say summing over lambda, some constant k lambda of phi of x sub lambda is equal to 0. That is, we have, these phi sub lambdas represent solutions to a differential equation, right? They might be sine of x and cosine of x for the harmonic oscillator, for example. It'll depend on the order of the differential equation, obviously. So we have this such that all k sub lambda is equal to 0 and phi of lambda is not equal to 0. then we have linear independence. Okay, so if we can find solutions such that they sum up to 0 in this way, then we have linear independence. What we can do is define something called the Wronksian. And I have to admit that this was the only time, the first and last time I went to office hours for complex, I think it was complex analysis, and the Wronskian came up. And it was clear that I hadn't read the book, because when I asked the professor about the Wronskian, he laughed and asked me if I had read the book. And I said, yes. And then he said, it's the Wronskian, not the Wronskian. And I thought, well, I'm getting it wrong. So I didn't come back to office hours after that, ever. Sorry. Anyway, W is a determinant, or a determinant of a set of functions that we can use not only to determine whether some two solutions or more are linearly independent, excuse me, but to also determine what the linearly independent second solution is if we know the first solution. And the idea comes from, well, if we have a set of solutions such that this is true, then if we take the derivative of these solutions, this will also be true if we take the second derivative. This will also be true, and so on. This is another way of saying that these solutions are going to be mutually orthogonal. We can, what we get then is that linear dependence, so dependence, is demonstrated for k sub lambda is not equal to 0 only if W is equal to 0. For the set of equations, basically if we solve the simultaneous set of equations, that is, if we set up phi 1, phi 2, phi 3 out to phi n, and then their derivatives, and so on, and we can keep this going down to phi sub 1 to n minus 1 out to phi sub n minus 1. If this is equal to 0, then we have linear dependence. And this means what we have to be careful. It's not just that it's 0 at a particular point, it's 0 over the entire range. That is the entire range of X. All right, so the usual example that we can consider is something straightforward. Let's say for y double prime is equal to y, right? We know that phi 1 is equal to x, and phi 2 is equal to e to the minus x. So, sorry, e to the x and e to the minus x. And if we wanted to test for linear dependence, we would then take e to the x and e to the minus x, that is phi 1, phi 2, then take their derivatives. That's just e to the x, and this is minus e to the minus x. Right? And if we did this, we'd get minus e to the x over e to the minus x minus e to the x over e to the minus x, which is not equal to 0. Okay. So in other words, our two solutions, phi 1 and phi 2, are linearly independent, which is another way of saying that this is a second order differential equation, right? We found both solutions. You can try the solution, for example, if phi1 is equal to e to the x, phi2 is equal to e to the minus x, and phi3 is equal to hyperbolic cosine of x, then we would have e to the x times e to the, and then e to the minus x, cosh x, and then the first derivative, e to the x, minus e to the minus x, sinh x, and then since we're dealing with three solutions, this is a third order differential equation, a solution to a third order differential equation. This would again be e to the x, this would be e to the minus x, and this would be, again, cosh x. And if you did, if you computed the determinant of this, which I'll leave as an exercise for fun and profit at home, you can show that that's equal to 0. And that shouldn't be a surprise. Hyperbolic cosine is comprised of a linear combination of e to the x and e to the minus x, right? So hyperbolic cosine, or our third solution here, depends on our two solutions, a linear combination of those two solutions. Okay, so the main point of this part of the lecture is use the Wronksian to determine whether you have a whether you have two, usually it's two, linearly independent solutions. Okay, so it's a diagnostic tool, and that's great. But we want to use it for more. We want to use it to be able to solve for that second solution. So now we're going to assume that we have one solution and find the other using the Wronskian. And we're also going to assume now our usual second order differential equation, y double prime is equal to p of x times y prime of x. Again, these are all implicitly functions of x, plus q of x times y is equal to 0. One way certainly for a second order differential equation, we know that the Wronskian, since it's the determinant of those of the solutions, say we have solutions y1 and y2, then this is going to be y1 times y2 prime minus y1 prime y2. This is just from the definition of that the Wronskian is the determinant of the set of those solutions, right? We don't know what y1 and y2 are yet. We're just setting up this relationship. And we know if we wanted to, we could take the derivative of the Wronskian. So that's y1 prime, y2 prime plus y1, y2 double prime minus y1 double prime, y2 minus y1 prime, y2 prime. But here we can take advantage of our definition of our differential equation. That is, y double prime is plus p of that p times y prime plus q. So we can rewrite this as y prime times minus p y2 prime minus q y2 minus y2 times minus p y1 prime minus q y. In other words, this is equal to minus p of x times y1 times y2 prime minus y1 prime y2. But that's just the Wronskian. In other words, this is equal to minus p of x times w. And I want you to stop and think about what we've done here. This is actually really pretty cool. We've taken a diagnostic tool and we have taken kind of a step back. Oops. And we've created a first order differential equation that we can probably solve, right? we have ultimately what we are looking at is y prime is equal to minus p of x w. In other words, y, or w prime, sorry, w prime over w is equal to minus p over x. Presumably, we can do separation of variables, especially if p of x is a simple function. And there's a special class of function or solutions in which p is equal to 0. That is when you don't have that, that first derivative of y. Okay, so this is a pretty neat thing that just comes out of the definition of linear independence. So what do we do with equation 25? Well, the idea then is to start solving this just by using this equation. So if we integrate from some point a to x, and we're going to drop these reference points in a bit because they're just going to be constants that we can normalize out anyway, we have essentially dw over w is equal to the integral from some point a to x of minus p dx, or the natural log of w of x over w of a is equal to this integral. Again, p is a function of x, or, and this should look familiar because this harkens back to last week when we were talking about general solutions for these differential equations. W of x is equal to w of a times e to the minus the integral from a to x of p of x1 dx1, where the x1s are dummy variables. Okay, that would be great if we were solving just for w, but what we want to solve is for a second solution, right? So now we have to look at what w means, right? So, but recall that w as a function of x is equal to y1, y2 prime minus y1 prime, y2, or, and again, this is just recognizing these patterns because we tend to see them a lot in physics, y1 squared times d dx of y2 over y1. So that means that we have d dx of y2 over y1 is equal to w at a, just a number, times e to the minus integral from a to x of p of x1 dx1 all over y1 squared. So y2 of x, remember, we're going to assume that we know what y1 is. Is equal to y1 of x, w of a, times the integral. Now, this is a little bit subtle, from b to x. We're now integrating. This is a different dummy reference point. Since we have a derivative over here, we have to take the integral of all of this, right? So this is the integral over x of e to the minus integral up to x2, oops, p of x2, p of x1 dx1, and now this y1 of x2 squared is inside the integral. In other words, we just integrated both sides, right? This is 28. D29. And that's our solution. That is, if we know what y1 is, oops, sorry. So if we know what one solution is, we can do this this integral, right? So if y1 is known, then we can put that into the integral. And if p of x is given, that's the differential equation, right? In the special case for p is equal to 0, this becomes a lot easier. Y2 of x is equal to y1 of x times the integral of x dx2 over y1 of x2 squared. Okay. The only, and that, so D30 and D29 are your pathways if you know what y1 is. And in fact, the other thing that we can do, and is often done, is that we could take this w of a and set that equal to 1. That's essentially means that we're normalizing the function so that because we're doing this integration from a reference point, we don't actually need to know what w of a is. So when you actually do question, when you look at solution or questions like this, like 7.22, you're just going to need the solution, the one solution you're given, and then plug that solution into D29 if p of x is not equal to 0, and D30 if it is. So for the oscillator problem, we have y double prime plus y is equal to 0. That means that p is equal to 0. And let's assume that y1 is equal to sine of x. We know that's one of the solutions, right? We'll start with, we'll do something where we know the answer, right? So y2, we used, in this case, D30. So y2 of x would be equal to y1, so that's sine of x, times the integral over x of dx2 over this first solution, sine of x squared, dx. That's equal to sine of x times minus cotangent of x. Some of these integrals might be integrals you have to look up, right? There's no guarantee that these integrals are going to be easy. But that means that this happily gives us what we expect, that is minus cosine of x. And then, as always, check back with substitution. And you can try that with other, you have one problem on the homework and there's one example. I did post, by the way, a sample exam on Moodle for the second exam. Even though it's a couple weeks away. There's a problem with the Wronksian on it as well, so you can practice that. All right, are there any questions about the logic here? To me, this is one of the coolest things, right? We take a diagnostic test, and because of the way we've written this diagnostic test, we can actually use this diagnostic test to find a second solution. So,
does this work out for higher dimensions?
Yes.
If you do 2 of the 3?
Mm-hmm. Yep. It's a little more complicated, but yeah. And one of the things that you can do too is this will work for series solutions, because you are generally, you're looking at integration of series solutions. There's the second half of the chapter on this, which I'm not going over explicitly in lecture, is how you do this with a series solution. But you can do this kind of integration with a series solution to find a second series solution. Yep. But as you can imagine, it's a little bit more complicated with higher dimensions, or higher order, All right. If there are no questions, then I'm going to put you back in your rooms for your weekly reflection. Remember, and this is just a reflection over the entire breadth of the topic on basically chapter 7, ordinary differential equations. So a main point, an example, and then you don't have to share, unless you want to, something that gave you a difficulty, but there is a link for you to write what your reflection is on the Moodle page. Please do that today at some point. It'll only take you a couple minutes, and it helps me figure out what else I can do to help make this class run smoothly and be the best class it can be for you. Okay? And you get 15% of your grade from it. So there's that. All right. Let's see. How do I do this now? Open all rooms. Go ahead and join. Okay. Got everybody? Okay. Awesome. Let's see. Let's see. Okay. What you got? What do you got? Anybody?
Ali and I talked about the main point being when a differential equation isn't separable, there are a lot of ways we can try finding solutions, like with integrating factors or the Frobenius method, or series solutions, or the Wronksian.
Okay, good. Anybody else? Yeah. Tom, are you raising your hand? You might as well jump in. You're muted. There you go.
Yeah. We talked about kind of how if you have ordinary differential equations set up and there's just no clear answer from there, assuming a series solution just makes things a lot easier.
Mhm.
And it'll often turn out that your solution isn't even a series, it's actually just a I forget what the word for it is, but like an analytic solution right there.
Right. I think that, I mean, one of the takeaways, I mean, certainly when I first studied this, is exactly that, that when all else fails, try a series solution. And if you're lucky, you can get it in closed form. That is that you find either the series will terminate, like the example we did today, or you'll recognize it. And sometimes it takes a little bit of effort to bend it into a way that you can recognize it as a function that we're familiar with, right? And that's one of the reasons why we started this class with series, infinite series, and then went back to things like Taylor expansions and binomial expansions of fundamental functions, because they show up quite a bit in these solutions for differential equations. Anybody else?
We talked about kind of like some of the other stuff we've done. You can turn these more complicated problems into basically algebra.
Yes.
It's just matching terms and all that.
Right. And again, one of basically the themes, if you go actually to the syllabus and look at some of the learning goals and objectives for this class, it's right there up front. Again, be creatively lazy. If you can take differential equations and somehow turn it into an algebra problem, life is so much simpler. And then often we see what comes out of that algebra is an intuition for the problem itself, in terms of a limiting behavior or just sort of fundamental understanding. We haven't done a lot of application in some of these homework problems. We're getting to more and more of that. In the homework this week, there are actually, I think, a couple of Schrodinger equation solutions. When we get next week to partial differential equations, we're going to use some of this stuff to look at Laplace equation and heat transfer and all of those good things. Okay, anybody else? One last thought?
Ali and I had a hard time thinking of examples of this because in all our past classes, they were almost always separable, I feel like.
Yeah, that's true. Some of the where this becomes more useful is when you start getting into those class of equations that arise from special functions. So Hermite polynomials, Legendre polynomials, Bessel functions, those kinds of things. And those tend to show up as pieces of partial differential equations. So if you remember from E and M, you ran into Legendre polynomials after you separated everything out and you were looking only at the theta term, for example. And if you just treat that as an ordinary differential equation because of the geometry of that solution, you end up with this weird thing that you need to do essentially a series solution to. So what you're going to be seeing are things like, and again, like the Chebyshev equation, all of those are specialized cases for different geometries and different assumptions, typically about either the solution to a Laplace equation or Schrodinger equation, basically a wave equation. So that's a really good point, is that up until now, you really haven't seen stuff that you couldn't separate, at least in some way. But this gives you the ability to do that in some of these applications, eventually in partial differential equations in particular. Okay, that's a great observation, and we'll get to use it next week. All right, we're out of time. Again, thank you so much. It's so good to see your faces, and I wish that you were here. If you have any questions, they'll be around, but have a restful midterm reading period and be safe. And like I said, I'll be around if you have questions. Otherwise, I'll see you online on Monday. Okay? Bye, guys.
Thank
Bye,
you.
Matt.
Yeah,
Bye,
bye,
God.
Matt.
All right.
Bye, Nick.
Oh, stop sharing.